Hello and thank you for watching my video. My name is Astrid Krasniqi. Today we will be talking CCNA Semester 1, Day 4. On this lesson we'll talk about IP addressing first, different kind of IPv4 network addresses, then IPv6 network addresses, then we do a different kind of connectivity verification. Part 2 represents a subnetting IP network, so we have to understand how to subnet an IP address, IPv4 address, and then addressing schemes, and the design and consideration for IPv6. Okay, so let's get started. Part 1, IP addressing. First of all is a binary notation. You need to know the binary notation refers to the fact that computers communicate in ones and zeros. All the communication between the computers or network devices is happening in zeros and ones. Now binary notation doesn't have number 2. It's all zeros and ones. We just use different kind of zeros and ones combinations to give a I don't know, display, letter, character, IP address, anything that we want to represent, any information that we want to represent in the computer world, we do it with the zeros and ones. For example, IPv4 or IP address on the computer. Now you need to remember IP addresses for the computers is like the names. They need to be identified with something. So IPv4 address is represented in 32 of these binary digits, either zeros or ones. So we have to be very familiar with how to convert these ones and zeros into decimal, from binary to decimal, and need to learn how to convert from decimal to binary. So let's learn that. Let's learn how to convert from binary address to decimal address. The first digit on the binary that we can use is 0. Now if we convert that 0 into decimal, it will equal to 0. The next digit that we can use in binary is 1, obviously. If we convert that digit into a decimal, it would be 1. So let's write 1 there. Okay, since we have run out of any different combination that we can use on this column only, now what we have to do is to extend the numbers, we have to move to the next column. So it will be 1 0. Now that digit will represent, for example, 2. Okay, so I have 0, 1, and then we run out of this column. Any different kind of combination that we can use. So we move to next column, 1 0. That will be 2. Okay, so the third number would be 1 1. If we convert that to decimal, that will be number 3. Now these two columns, again, we have run out of every different combination. There's no any other combination that we can use here to come up with a new different number. So because we have run out, we move to the next column. So that will be 1 0 0 0. So this digit will represent, these numbers that will represent 4 in decimal. So 1 0 0 in the binary will be equal to 4. Okay, then we will try and use every different kind of combinations until we run out. So that will be 1 0 1, which will equal to 5. So I'll write down 5 here. Then a different combination that we could use here with these 3 different columns is 1 1 0. That will equal with 6 6, sorry. And then a different combination that we can use with 3 columns is 1 1 1, which that will equal 7 now. And we have run out. There's no any other combination that we can use with these 3 columns here. So when we run out of space, what do? We move to the next column. So 1 0 0 0. Now that will be 8 now, and so on. You can see there's a pattern. If you go on next one, it will be 1 0 0 1. That will be equal to 9, and so on. So okay, I cleaned our table, left nothing in it. It just out our numbers on the top. These are the digits they're going to be representing our bits. Okay, so to convert from binary to decimal, it's very simple. You add in the ones, whatever there is 1 there, you add that number, and you ignore the zeros. Ones, you have to look at where the position of one is. For example, if we look at like for example in the decimal, yeah, in the decimal number, say I give 123. Now that number is 123. Why? Because this bit here is representing hundreds, so 100. This is representing tens, so there's 20, and these are the units. There's number 3. So that's why we know that's 123 in decimal. So same thing goes with the binary. You just need to know where the position of that bit is so you can convert it. So if I give a number, for example, binary number 0, 0, 0, 1, 0, 0, 1, 1. Okay, so all I have to do is ignore the zeros. Don't have to think about them. But I have to add the ones. This one here, it represents 16 bits. So because you can see there's a 16 bits. Okay, so this one, it's like 16 bits. Plus this one here represents 2 bits. So that's 16 plus 2 is 18. Plus 1 is 19. So this is 19. Okay, that was easy. To convert from binary to decimal, you just add in the ones. Look at the ones, the position of one, where it is, and that will be easy to identify what number it is, and then we can just add them. So, for example, let's take another one. So 1 0 0 0 1 0 1 0. Okay, so what is that in decimal? Well, let's see. This bit here is representing 128. Okay, I keep that in mind. I ignore all these zeros, all these 3 zeros, and then I have another bit here. So that represents 8. So 128 plus 8, 136. Okay, I ignore this because it's 0, but I have to add this. This bit is 2. So 136 plus 2 is 138. So this is 138. Okay, now they're easy. You just look at the ones. Whatever the position of that one is, we have to add that. So for example, let's say 0 0 1, so 0 0 1 0 0. Okay, how easy is to convert this? Well, first of all, I'll just ignore these 2 zeros. Then I move to this one. This bit represents 32. Okay, I have that on mind. Plus this bit is representing 4, so this is 36. Excellent. So this is 36. Different kind of combinations. All you're doing is you add in the ones, you ignoring the zeros. So the minimum number, the lowest number that we can have in binary, it will be 0. So this will equal to 0 if they're all set to zeros. Now if they all set to ones, what do you think that would be? Minimum. Well, if they all set to ones, that's the maximum. So this bit is 128. 128 plus 64, it's 192. Plus 32 is 224. Plus 16 is 240. Plus 8, 248. Plus this bit represents 4, 252. This bit represents 2, so 254. Plus this bit represents 1, so 255. So 255 is the maximum. So in 8 bits, minimum is 0 and the maximum is 255. So 255. That's total of 256 combinations, because all zeros is a one kind of combination, and that's up to 255. So plus 0, which is a combination, is 256 different kind of combinations. So for example, the first one was 1, then the second one was 1 0, I should say that's number 2, 3 1 1, then that was 1 0 0 4 and so on. But the maximum you're going to reach is all ones, 255. Right, let's go back now. Sorry, converting from decimal. To convert from decimal to binary, it's similar, just the other way around the steps. Okay, So first we have to think of, okay, okay, I've cleaned the table again. So for us, now we want to convert from decimal to binary. Okay, gonna pick up a number. Now, for example, the decimal number of 200, I want to convert this number into binary. First thing I have to do is look at this bit here, the leftmost bit, which is the highest number there, 128. If it's equal to or lower than 200. If it's equal to or lower than 200, I'll put 1. In this case, 128 is less than our target of 200. So we put 1 there. Now we have to take away 128 from our target number. So our target number is 200 minus 128. That will leave us with 72 left. 72. Okay, great. Our new target is 72. So we look at the next bit on the line, 64. 64 is lower than our new target. So if it is lower, then we'll put 1. Because we put 1 there, we have to take away 64 from our target. So 72 minus 64. Okay, so 72 minus 64, 8 left. Now we have 8 left. 32, the next bit on line, 32 is higher than 8. Because it's higher, it's a larger number, we have to put 0 there. Now we move to the next bit, which is 16. 16 again is higher than 8, so we put 0 there. We move to the next bit, which is representing 8s. Now 8 is equal to our new target. Because it's equal, we put 1 there. 8 minus 8 will equal to 0. So because we have a 0 left, everything else will become 0. So 0, 0. So 200 in decimal. To convert that in binary will be 11001000. That's our 200. Okay, the next digit I want to take is 50. Decimal number 50. I want to convert that into binary. So we have to look at the leftmost bit, the highest number there, 128 bits. If it's lower than our target or equal, we put 1. But in this case, 128 is not lower than our target. So we have to put 0 there. We move to the next column, 64. 64 is higher than 50, so again 0. 32 is lower than our target of 50, so we put 1 there. Now we have to take our 50 minus 32. So 50 minus 32 will leave us with 18. Okay, so the next bit, which is 16, our new target is 18. 16 is lower than our 18, so we put 1 there. We take away 16 from 18, so we put 16. That will leave us with 2. 8 is higher number, so we put 0. 4 is higher number. 2 is equal to our new target, so we put 1, and then it will be 0. So 50 in binary would be 00110010. Okay, the next number, let's take another number, say 141. 141, I want to convert that into binary. To do that in binary, we look at the leftmost bit, which is the highest number, 128. If it's lower than our target, which it is, 128 is lower than 141, so we put 1 there. Because we put 1 there, we have to take away 128 from our target. So 141 minus 128. Okay, so 141 minus 128, what is it? 13 left. Okay, great, we have 13 left. 13 is our new target. 64 is higher than 13, so we put 0 there. 32 is a higher number than 13, so we put 0 there as well. Then we move to the next one, next column. We look at 16. 16 is higher than 13, so we put 0 there as well. Now the next column, which is 8, this represents 8 bits. So 8 bits is smaller than our 13 target, so we put 1 there. But we have to take 13 minus 8, which will leave us with 5. 5 left. 4, the next number, 4, is lower than our target, new target 5, so we put a bit there. Because we did that, we have to take away 4 from our target, which will leave us with 1. 2 is higher than our new target of 1, so we put 0 there, and 1 is equal, so we put 1 there. So 1 4 1 in binary is 1 0 0 0, sorry, 1 0 0 0 1 1 0 1. So that's how it's to convert from decimal to binary and from binary to decimal. I would do this, even though it seems very simple. I would do this a few times and try not to forget it. This table, 8-bit table, you really need to write it down, and in the front of the page somewhere, so when you do the calculation, it's always going to be close to you. Okay, so we learned that everything in the computer world is happening with the zeros and ones. The communication with the zeros and ones. The computers have an IP address, which is like the name, the identification. That is in zeros and ones, 32 of them. And we learned how to convert from binary to decimal, and we convert from decimal to binary. Network portion and host portion of IPv4. So the subnet mask does not actually contain the network or host portion of an IP address. It just say where then look for this portion and give an IP address. Okay, so let's have a look. If we have, for example, an IP address 192.168.100.50, this is IPv4 address, IPv4. Now this address is going to have a subnet mask with it, so it has to have a subnet mask 255.255.255.0, for example. That's the subnet mask that's coming with it. Now the subnet mask is telling what part of the network, what part of the IP address is a network portion and which part of the address is a host portion. For example, let's convert this into binary. So 192 is 1100000000. 168 is 1010 100. 100 is 3296 100. So 0 64 plus 3296 0 0 100. Okay, that's 100. And 50 40. Okay, so 0 0 1 1, that's a 48, and 0 0 1 0, that's 50. So 32 48, I'm just trying again, 50. Okay, that's fine. Now this IPv4 address needs to have a subnet mask to tell which portion of that is a network address and which portion of that is a host address. Okay, so if we have a subnet mask, the default subnet mask 4/24 or 24 ones, then what is this telling us? The subnet mask is very important. It's telling us, okay, well, this side, left side, upper ones, because that's a network area. This side on the right, upper zeros, because that's a host area. So to identify which is a network, upper ones. For the host, upper zeros. These ones on the left, they have to be contiguous. They have to be on one after another. You can't have a 1 in the middle there somewhere. It's not allowed. It's a subnet rule that says ones are on the left and the zeros are on the right. So it's identifying, okay, well, this area of the IP address is a network and this area is a host. So that's the job of the subnet mask, just to tell us network, host, portion. So this is a network portion and this is a host portion. The subnet mask will do that by putting ones for the network and zeros for the host. Okay, so if this is our host area, this is our network area. So what will be our network address? Well, network address will be 192, if I convert this back to decimal, 168.100. That's our network address, 192.168.100, because the subnet mask is telling us. And the last bit I can just say 0, because we're not really interested on the host. If we want the network ID or the network address, we not care. We don't not care. I'm not saying care, but we're just not concerned at the moment with the host portion. So I can just say the address or the ID will be 0, 192.168.100.0. That's the network ID. Okay, excellent. Now, if we had, for example, if I convert this back to decimal, I would say 255.255.255.0. Okay, I can represent it. I can write it like that in binary. I can write it in decimal, or I can say prefix length. Prefix length, for example, 24. What is this 24 now? Okay, well, 24 telling us how many ones are there. There's 24 ones. There's 8, another 8, 16, another 8, that's 24. 24 ones. Okay, so prefix length is just telling us how many ones are there. If, for example, we said, I'll put another 8 zeros here. 1, 2, 3, 4, 5, 6, 7, 8. Now the subnet mask will change to 255.255.0.0 in decimal. The prefix length will change to 4/16. There's only 16 ones. But now we are saying there is where the separation is. So this bit here is a host area, a host part. Since that's a host part, now here the network is only 192.168. Okay. Now, IPv4 address is 32 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. This is IPv4. 32 bits. With 32 bits, we can have just over 4 billion different combinations of zeros and ones. Now, it is not easy to say, okay, well, this is 4,345,000 and so on. It's really hard. So what we did is we separated, not the computer, it's for us, this is for our use. We separated in the 4 portions. 1, 2, 3, 4, 5, 6, 7, 8. So we divide it into 8 bits or bytes. 1, 2, 3, 4, 5, 6, 7, 8 dot 2, 3, 4, 5, 6, 7, 8 dot, like this. Now we have separated this IPv4 address, 32 bits, into 4 portions. Now each one there's 8 bits, or a byte you could say. Now this is called octet. Octet. So 4 octets. Yeah, 4 octets. Okay. Now I want to show you how important is the subnet mask. For example, I'm going to give you 3 addresses: 192.168.10.10, 192.168.20.30, 192.168.30.30. Oh, sorry, yeah, that's it. 192.168.10.10, 192.168.20.30, 192.169.30.30. Okay. Now, the subnet mask. If I have 255.255.255.0, what do you think out of these 3 IP addresses, which one will be able to communicate with each other locally? Locally meaning that they don't have to go through another network. If the address is the same on the same network, then they will be able to communicate with each other without going through the router or through the layer 3 device. So 255.255.255.0, it says 3 octets, first, second and third are network. So this is network, this is a network, this is the host. So now all three of them is different, so they will not be able to communicate with each other. They will need a layer 3 device. Even if they are connected right next to each other in same switch, you give these addresses, they won't be able to communicate. They need a router, or they need a gateway. Now if you change a subnet mask, for example 255.255.0.0, what this says now, the first two octets are network, one octet, second octet, third and fourth are a host. So I can separate them like this. Now these two are the same, 192.168 192.168. So it means that these two devices, they can communicate with each other without the help of the router. They will not be able to communicate to the 169 because that's a different address. To be able to communicate with them over this IP address, they need the help of the router. Okay, fine. Now if I go and change the subnet mask into 255.0.0, what I'm saying is only the first octet is the network ID or the network, and as you can see, all three of them, they share that. So because they share that, they will be able to communicate with each other without the help of the router, all three of them. So as you can see, all you can do is change the subnet mask, and you can make the devices on the network communicate with each other or not communicate with each other to appear on a different network. This is a default class C address or a subnet mask, so we will learn how to change them very soon. Okay, so the subnet mask, the role of the subnet mask is to tell us which part of the IP address is a network and which part of is a host. So if we have, for example, an IP address, say, let me get another address, 200.100.50.5. Now, as a network device, I don't know where is the ID, where is the network ID, and which portion is the host. Is this the host, or is this all those two, and so on? It needs a subnet mask. So 255.255.0.0. Now this subnet mask is telling us this part here is a host area, so host and network, host, network. Remember, 255 is like writing 8 ones, yeah? 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, and then the host portion, zeros, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. So the subnet mask will place ones for the network and zeros for the host. Ones, they have to be on the left, zeros, they have to be on the right. You can't mix and match. You can't. This is against the subnet mask rule. Valid subnet mask. Okay, so valid subnet mask. What we can have. I'm gonna use the last octet. Okay, this octet only. All right. Now, if I use only that octet, I could have all zeros. Yeah, 3 4 5 6 7 8. If I have all zeros, then that will be 0. If one of the bits has changed, let me just write this at once as well. 1 2 3 4 5 6 7 8. Okay, if one of the bits has changed into 1, right? If you borrowed 1 bit, then the address will look like this: 1 0 0 0 0 0 0, and the oops, not that. That bit represents, if you should know now, the binary to decimal. That should be 1 to 8. If you have borrowed 2 bits, for example, then that will be like this. The 2 bits, you add them together, so 1 to 8 plus 64, that will be 192. so 192. If you borrow 3 bits, for example, if you add these together, so 128 plus 64,192 plus 32 is 224. If you borrowed 4 bits, there's not 2 there, that would be 240. If you borrowed 5 bits, $248. If you borrowed 6 bits, for example, 252. And then 7 bits with a 7 bit, 254. And all ones, 255. Okay, so this is your subnet mask. Let me just try and fix these. Okay, what you could do, write these down, these numbers. This is all your subnet masks they could be. So if they all set to 0, then it will be 0. If the first bit is taken and the rest are zeros, it's 128, then 192, 224, 240, 248, 252, 254, and 255. These are valid subnet masks. You're not going to have a subnet mask, for example, 210. It's never going to be. So for example, 255.255.210.0. Not allowed. Can't do that. So these are the numbers they're going to be. For example, again, you can't have 255, 255, 255, 2. Not way. No way. So they could be .0, .128, .192, .224, .240, .248, 252, 54, and 55. Like this, yeah. Right. This exercise we took is for last octet, but it could be on the second octet or third octet, for example, 0.0, 128.0, 192.0, or 252.0, and so on. Or it could be on the second octet, for example, 128.0.0, 192.0.0. You have to remember the ones they're going to be on the left and the zeros on the right. So you're never going to have 255.192.0.128. Not allowed. So it's going to be always like this. And class A, for example, if you remember, that will be 255.0.0. The prefix length we already talked about. The prefix length talks how long or how many ones are there. So for example, here we have /24. That's our prefix length, 24. If we have borrowed 2 ones here, for example, 1, 1, the prefix length will be 26. It's just telling us what number, how many ones are there. For example, a prefix length of 17, that will mean, okay, there's 17 ones. So that's 8, 16, and 17. And the rest are zeros. 1, 2, 3, 4, 5, 6, 7. I'll get rid of these. And that's 17. Or, for example, prefix length of 22, that will be 8, 16, 17, 18, 19, 20, 21, 22. So 2, 3, 4, 5. Okay, done. 3 different ways of representing the subnet mask. We can say it with ones there and zeros. We can say it with prefix length, or we can convert it. There will be, this one will be 255 dot 255 dot, this one is 252 dot 0. 3 different ways of explaining the same thing, the subnet mask. I can write it in binary, prefix length, or in decimal. 3 ways is correct way. So IPv4 network, host, and a broadcast. In here we talk about first host and last host address. Okay, so if I look at the say another address 192.168.100.0 with the subnet mask 255.255.255.0. Now this bit here, you should know that's a network ID. That's a network, and this one here is the host, because the subnet is telling us. So it's saying that area, that part is a network, and this area is a host. Okay, so what I'm gonna do, I'm gonna use only the host portion. Now if I write down 192.168.100. I'm gonna write down the host portion on the binary. So 1, 2, 3, 4, 5, 6, 7, 8. I'm writing the host portion on binary and the network portion on the decimal. So I'll write 2, 4, 6, 8 zeros on binary. So that's your starting point. Then you will do different kind of combinations up to when you reach, for example, when you reach ones. So 1, 1, 1, 1, 4, 6, 7, 8. So different kind of combination. Now here is your where you can use the addresses they are valid for you inside here. So this is 192.168.100. It's not gonna fit 100.0. I'm just gonna write these one a bit smaller so they will fit. Okay. Now this one, it will be 192.168.100.255. Okay, I want to write these maybe in red or something so you can identify them. Okay. Or the next network in red. That's a network. Yeah. Let's write the network in bold and red. So that's your starting point. 192.168.100 and all zeros. That will end up with this is the IP address. So that's the network ID. We will do a different combinations until we reach this number, 192.168.100.255, because they will have all ones. Now the first address, one second, trying to fix it now. Okay. So the first address that will be usable, we'll put 1 there. We start with 1. That's our first address. And the first address, or first valid address, will be 192.168.100.1. That's our first address. Last address is this address minus 1. So that address minus 1, this will be 0 here. And if you convert it back, if you add all these ones, apart from this is 0, it will be to 254. So we need to know this is the first valid address and this is the last valid address. Everything else in here in the between, there will be different kind of combinations until we reach the last valid address. Okay, we're going to talk a lot more about the first valid address, last valid address, network ID, and the broadcast. Bitwise and operation. So first, now we need to know how the computer knows is when he wants to send data. Is it on its own network or is it in somebody else's network, a remote network, for example? What it's going to do is going to convert bitwise conversion. So bitwise and operation. So where one plus 1 will equal 1. 1 plus 0 will equal 0. 0 plus 0 will equal 0. Pretty much everything else. So 0 plus 1 will equal 0 as well. Only 1 plus 1 equals 1. Everything else equals 0. So say that we're using the same IP address that we had before. What was it? Where was it? Here. This address. Okay, let's use that. Configure 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay, this was 100.50. All right. Now this is the address of this PC. One PC, and it's going to try to find out what is my network address, what is a network ID, where it's going to put ones and zeros, a bitwise conversion. So it's going to use like this, where 1 and 1 equals 1, and then everything else will equal to 0. So this bit add with this bit, so 1 and 1 equals 1. Again, this bit add to this bit will equal 1. Because it's 0 here and 1 here, that will equal 0. And again, we'll continue 0, 1, it will equal to 0. And we'll do for the rest. All zeros and 1 is going to equal to all zeros. This bit is 1, so it's going to add to this bit, that will equal 1. 0 and 1, 0. 1 and 1, I got 1. 0 and 1 equals 0. 1 and 1 equals 1. And then the rest are 3 zeros with 3 ones equals all zeros. 0 and 1 will equal 0. 1 and 1 will equal 1. 1 and 1 again 1. 0 and 1 is 0. 0 and 1 is 0. 1 and 1 is 1. Then 0, 0. 0 and 0 is 0. Again 0. 1 and 0 is 0. 1 and 0 is 0. 0, 0, 0. 0 plus 0 is 0. 1 and 0, 0. And 0, 0, 0. So now we just found out, this PC has found out what is the network ID. If we convert this back into decimal, this will be 192.168.100.0. Now this PC says, okay, now I know what is my network ID. Where do I belong? So I do live on this network ID, 192.168.100.0. And I will send any packets on my local network. It starts with these 3. I know I'm going to send them directly. I don't want to send it to layer 3 device. Assign an IPv4 address to a host. To assign IPv4 address to the host, you will go to the control panel, and in the control panel you go to Network and Internet, Network and Sharing Center, then change it after settings here. Okay, so here I've got some virtual, local, and the wireless network here. I'm going to use this one that is disabled, so I choose a VMware. So right click, go to Properties, and then choose TCP IPv4 and the properties of that. This is given a static IP address. If you want to give it a dynamic IP address or through DHCP server, you will click this. Now when I click that, alternate configuration comes along as well. The reason why is alternate configuration. If you can't communicate with the DHCP server, you will give yourself an IP address even if DHCP server is not there. By default is automatic private IP address. So automatic private IP address is Microsoft unusable addresses which start with 169.254. They are reserved only for this purpose. Or you can configure one for yourself. But that was if you try and use a DHCP server. If you want to use it static, you will say use the following IP address, give an IP address, for example 192.168.100.50, default subnet mask we had early. So for example, the subnet mask, if you remember, it could be 0, could be 128, could be 192.224. It's okay, all of these is fine. How about if we try and give something that is not there? It shouldn't allow us. Once we click OK, it will says invalid subnet mask entered. Okay. See, the subnet mask has to be contiguous. Please enter valid subnet mask. Okay. Cancel that. If you can see grayed out like this, means it's disabled. So to enable them, you right click and say enable. And then the network card will be enabled. Okay, I'm going to disable again because I don't need it. Okay, we just saw how to assign a dynamic IPv4 address to a host as well. Now unicast, broadcast and multicast transmission. Now unicast is when two PCs they communicate with each other. That's called a unicast. So for example, say I'm going to grab two PCs here. So one PC and I'm going to use paint. So here, one PC communicating with another PC, that's considered a unicast transmission. So where is it? Let's use this. There we go. That's a unicast. If you talk to everybody, everybody on the network, then that's called a broadcast. So for example, trying to send a message to everybody here. I've got 3 PCs and I'm going to send a message to all of them. Then that's called a broadcast message. Now if you send a message to a group of PCs, now for example, not to everybody, not to that, you're only sending it to these 2 machines here. That's called a multicast transmission. So unicast, let's go through them. Unicast was 1-to-1. Multicast is 1-to-many. So for example, many, you divide them into groups and you send a message to the group. And you have a broadcast message, that's 1-to-all. So if you want to send a message to everybody, then that's a broadcast message. If you want to send this message to another computer, that's a unicast message. Multicast is to a group of computers. Public and private IP addresses. Now IP addresses, if you remember, we have different classes. So we have class A, class B, class C, class D, and class E. The range of class A is from 1.0.0.0 all the way to 126.255.255.255. That's class A. Now class A has 1-to-7 as well. So 1-to-7. This is reserved for loopback testing. So if you install the network card, you install the driver, you want to test everything is working correctly, you ping that address. Ping 127.0.0.1, for example. Class B starts with 128.0.0.0 and goes to 191.255.255.255. Class C is from 192.0.0.0 and it goes up to 223.255.255.255. Class D, this is reserved for multicasting. So this goes from 224.0.0.0 and it goes to 239.255.255.255. Class E, which is reserved for future research, it goes to 240.0.0.0 and it's all the way up to 255.255.255.255. But anyway, this we can't use it because it's reserved for future research. So can't use it. This address here is reserved for multicast. So equals multicast addresses. Now we're left with class A, B, and C. That's the full range. 1.0.0.0 up to 126.255.255.255. For class B, it's 128.0.0.0 up to 191.255.255.255. And class C, 192.0.0.0 up to 223.255.255.255. And 127, we already said this for reserved for loopback testing. Testing your network card you installed it correctly. The reason why they are in different classes is to, well, it was made for example, class A, major networks, big networks, and class B, medium size, class C, small networks. That was the idea. So class A supports around 16.7 million addresses, more than that, around just above 16.7 million addresses. Each class. Now each class B supports just over 65,000 addresses. Class C supports only 254 addresses. So that's why we have the different classes. But now it's all classless, so we don't need to worry about classes anymore. We need to know them, but we just don't purchase IP addresses depending on the class. Now each class has got a private range as well. Now this is a public range, and each class has got a private range as well. So for example, class A has got his own private range, class B has got the private range, and class C has got private range. So I'm going to write down private here. Private range for class A is from 10.0.0.0 all the way up to 10.255.255.255. Class B, the private range is 172.16.0.0 all the way up to 172.31.255.255. Class C, private range is 192.168.0.0 and that goes all the way up to 192.168.255.255. This is a private range. That's the full range, and that's the private range within the full range. So if you get an address, for example, say you get address 172.28.15.1, is this a class? Is it private or public IP address? Now, because it's within this range here, now that's considered a private. 172.28 is here, between these two. So, yeah, that's a private. 32, for example, 172.32, it's a public IP address. Okay, so what's the difference between private and public? So, private, we can use them within our network only. So, public, it's it's on the internet. So, for example, let me grab. Let's choose this. Okay. Okay. Now, if this is our network, for example, this is our small network here. Now here, put this on top. Within this network, we can use private IP address. We can use public IP addresses, but we don't have to. Because if we want to do that, imagine that we have 100 computers here. We can't buy each computer have a public IP address. So here within our network, we have hundreds of computers, but we can all use a private IP addresses. So here we can use private. Now, when we go to the internet, this interface here that connects to the internet, this interface cannot use a private IP address. This has to be used a public IP address. So I'm going to write it here. Public. So I'm just going to increase it a little bit. Okay, excellent. So when we go to the internet, boom, public. Now in the private range that we had, we can use any addresses. For example, if you use 10.1.1.1 or 0/24. This is our private range that we choose to use. Now this is ABC, the company abc.com. Now if there's another company, something else further down here, so let me just add another network down here and grab a router here. Router and a PC. Now this company can use a private, well, they will use a private IP addresses here within their network. Now this company is xyz.com, and these guys are choosing 10.1.1.0/24 to use that IP address. That's okay, that's fine. That's why the private IP addresses are very popular, are very used, because even though that we are using the same IP address, but because it's on private on the local network only, it doesn't go to the internet, they can be reused. The private IP addresses can be reused again and again and again. That's why we still have IPv4. When this address, or for example, a packet comes from this PC, wants to go to the internet from here, wants to go boom to the internet, send it to the internet. This router here is going to do something called NAT, Network Address Translation. So NAT is going to translate any private addresses coming from this network to public address. Public address, they have to be unique. So you can't have two public addresses the same on the internet. So the router is translating private to public, sending anywhere in the network. When it comes back, it's translating from public to the private address. So these private addresses are kept secure from anyone in the internet. Plus, we are saving the numbers of public IP addresses that we need to purchase. We have a different special use IPv4. Special use IPv4 addresses. Well, first of all, we already talked about some of them. So there's a network ID address. That's a special address, the address that we can't use. With this address is like we represent ourselves, 192.168.100.0. This is our network ID. Everybody will know, okay, this address is coming from that network. The second special address is a network broadcast address. Network broadcast address says if you want to talk to everybody on this network, you send it to this address. For example, 192.168.100.255. This is a special address. We can't use this address because this says that if you want to talk to everybody, you send this address. The special address, another one is a loopback. Loopback address. Now, loopback address is anything that starts with 127/8. So 127.0.0.1, .2, .3, .4, so on. .255, they're all loopback, reserved for the loopback testing. Then we have a link local addresses. Now we already talked about these link local addresses. They are assigned from Microsoft. So they start with 169.254.0.0. If you cannot communicate with the DHCP server, you will assign itself, or the computer will assign itself, a linked local address in the address from 169.254.0.0 up to 169.254.255.255. That's a linked local address. Then we have experimental addresses, reserved. So experimental addresses. So for example 240.0.0.0, and we said that they go up to 255.255.255.254 addresses. And then we have a test net addresses. Now these are reserved addresses for teaching, learning purposes, not usable addresses. And these are 192.0.2.0 and all the way up to 192.0.2.255. These are reserved addresses. We cannot use them. Okay, so these are the special addresses. Legacy classful addressing, we already talked about legacy. We have class A, B, C, and D. E is not used, it's reserved, and D is for use, reserved for multicasting as well. IPv6 network addresses. So the need for IPv6. Well, why do we have IPv6? The reason is that IPv4 is running out. In about 1 to 5 years, it's predicted that it's going to totally run out of IPv4 addresses. So it is successor to the IPv4, and depletion of IPv4 addresses space has been the motivation factor for moving to IPv6. Now IPv6 is not a new protocol. It's quite old now. So it's been started in 1990s, and we are transitioning from IPv4 into IPv6 now. Projections, we can see that between 2015 to 2020 we're going to run out of IPv4 addresses, so we're going to need them. And the reason is because the increasing internet population. With now with IPv4 we can have 4.3 billion addresses, and including the private addresses that will increase the numbers a little bit. But with IPv6, because it's using 128 bits, we can have 340 decillion addresses. That's a lot of addresses. In IPv6, that fixes some of the limitations. For example, including enhancements on ICMPv6. So IPv4 and IPv6 coexistence. Now there's no set date when we're going to move from IPv4 to IPv6. Maybe it should be. It's better if we say, okay, 1st of January 2016, we are all moving. No, there's no date. So everybody's moving as they have to. And that's why the move from 4 to 6 is being very slow. So we have to, for example, make sure that they live, because some people they already moved, some they're about to move, and some they're not moving. But they have to live together. Coexistence between them two, we have 3 methods. First is dual stack, which a router will support, or network device will support IPv4 and IPv6. Either way, it will be able to communicate. Then we have a tunneling, where we can tunnel. For example, our network, our company has moved to IPv6, but the internet service provider has not. But we can tunnel through the internet service provider through IPv4. We can tunnel IPv6 packets. And then we can do the translation as well between IPv4 and IPv6 translation. IPv6 uses hexadecimal numbering system. Now, hexadecimal numbers, they go 0 to 9 A, B, C, D, E, F. Okay. Now, for example, this is hex. We have 0, 1, sorry, 2, 3, 4, 5, 6, 7, 8, 9. And then we have A, B, C, D, E, F. Now, it doesn't matter. It can be a lowercase letters or uppercase letters, is fine. Now, hex 0 will be obviously in decimal. So I'm going to write them here on decimal. 0, then we have 1, 2. I don't need them to write them. Up to here, it's all the same. So 9 and so on. Then we have 10, 11, 12, 13, 14, 15. So 0 to 15. That's base 16. Because 0 is a digit as well. Don't forget that as well. So here on the left we have a representation on hexadecimal digits. On the right we have a decimal. So 0 to 9 is the same. Up here is the same. Then we have A, which is 10, B 11, C 12, D 13, E 14, and F 15. Okay, now one hexadecimal digit we can represent it in a binary as well. So sorry, binary. What would be 9? So on the binary digits, it's only 4-bit binary, yeah? So we have, for example, remember the table 128, 64, 32, 16, 8, 4, 2, and 1. Yeah. Now, because we can represent any hexadecimal digits only on the 4 binary number, we don't need the other 4, yeah? So I'm going to delete these bit here. So I'm going to leave 8, 4, 2, and 1. Now, what would you represent 5, for example, in the binary? So 5 in binary will be, okay, well, nothing on 8s, so 0. 1 on 4s, nothing on 2s, and 1 on 1. That's a 5, yeah? Now, A, for example, or 10, I'll put 1 in 8s, 0 on 4s, 1 in 2s, and 0 on 1s. That's 10. So A in hexadecimal is in binary 10, 10. F in binary would be 1, 1, 1, 1. So any hexadecimal digit you can represent it with 4 binary digits only. Now IPv6 address representation. Now if you have, because they are represented in hexadecimal, so let's have a look. If you have 2001 db8, sorry, let's write down 0 db8, 1, 2, 3, 4, 4, 5, 6, 7, 8, 1, 2, 3, 4, yeah, okay, then 0, 0, 1, there's a lot of zeros in IPv6, 0, A, 0, 8, 0, 1, 0, 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I did 1 too much. Alright. Now, 1 digit here, it's representing hexadecimal. Now that digit in binary is 2, yeah? So 0, 0, 1, 0. It's just that 2. That 2 there is this. Then the 0 is obviously it's going to be 0. Then another 0, 0, 0, 0, 0, and then the 1. Okay, so each digit in hexadecimal is representing 4 bits. 4-bit. So 2 equals 4 bits. Or 0, 0, 1, 0. And then 0, another 4 bits. That is 0, 0, 0, 0. then the other 0, then 1 equals another 4 bits. So that would be 0, 0, 0, 0, 1. Yeah. Okay. There you go. 2001. So 2001. Each one is representing 4 bits, and we can continue that with all the bits. Now IPv6 is 128 bits. So 4 plus another 4 is 8, plus 4 is 12, plus 4 is 16. So it's divided in 16 bits. So this here is 16 bits. So between the columns there's a 16 bits. So here there's a 16 bits. Okay. Now they are called 16 bits. Each 16 bits is called a hextet. Hextet. Now hextet, there's 8 hextets. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 hextets. So 16 times 8, that will give you 128. 128. Okay, let's use a calculator. Let's try it. Yeah, didn't find it. So 16 times 8, 128. Excellent. Okay, need to remember one of them is called a hextet, and there's 8 hextets in IPv6. So that will be 128 bits. 1 to 8 bits. Now it's really difficult to write all this down like this. So what we can do is the leading zeros we can remove. So the leading zeros, not the trailing, the leading. So 2001 colon. It's represented in column IPv6. Not dot, wrong, dash, wrong, semicolon, wrong, colon. Now the leading zeros we can remove them. So we don't have to write down that. We can just write down DB8, another colon. Now here we have 4 zeros. So we can't take all the 4 off at the moment, just the leading zeros. So the first 3 zeros we take them off. 1, 2, 3. We take them off. We write the 4th one. So let me just write here another 0. Again, 4 zeros. We can't write them all 3. We just write the last one. Sorry. Then we have 0, 0, 0, 1. So the first 3 leading zeros we can remove them. Boom, boom, boom. Take them off. Just write the 1. Now we have 0A, 08. Well, we can remove the 0. We can just write A, 08. So if there is a 0 in the between, you can't remove that. Now we have 0, 1, 0, 0. The leading 0 we can take it off, but the trailing zeros we have to write them down. And again we have 0, 0, 0, 1. We can just write 1. So this address we can write it down like this: 2001 DB8 0, 0, 1 A08 100 1. Excellent. Much shorter than that address on the top. Okay, now one more thing. Any contiguous zeros we can represent it with a double colon. So for example, we can write 2001 DB8 double colon 1 A08 100.1. Now how do I know how many zeros are there? Well, I told you earlier, there has to be 8 hextets. So if we count 1, 2, 3, 4, 5, 6, there's 6 hextets here. So here there might be 2 missing. There has to be 2 missing. So 1, yeah, 2. 1, 2. There's 8 hextets. Now this double colon can be used only once. So let me take another IPv6 address. So for example, 1234, 1234, 121, 1234, 1234, 1234. So 1234, 123, and right. 1234. Okay, I'll go hex 8 hex. 1, 2, 3, 4, 5, 6, 7, 8. 8 hex sets. Now this one I can write it like this. Leading zeros, miss them. 2001. There's 4 zeros there, so there's 4 zeros in this hex set, so I'm writing it just as 0. Colon. Another 4 zeros, I can just write it as 0. Colon. 0, 0, 1, 0. So I have to write 1, 0. I can't write down, take away that 0, the trading 0 off. Another 4 zeros, so I can write it 0. Another 4 zeros here, so I can write another 0. Another 4 zeros, okay, so I'll write another 0 here. And I got 3 zeros and 1, so I'll write 1 in there. Okay, so that's a compressed version, where you're compressing all the leading zeros. But now we have 2 continuous zeros. So we have 0, 0, and on this side we have 3 hex sets, which are continuous zeros. Now this is wrong if you do it like this. Okay, this double colon has to be used only once. Because now, okay, I know there's 3 hex sets here. So there's 5 hex sets missing. But I don't know if there's 3 hex sets on this side missing, and 2 on this side, 4 on this side and 1 on this side, or 1 on this side and 4 on this side. So there's no way for a network device to find out. So that's why we can use it only once. If you use it left or right, it doesn't matter, but it can only be used once. So if you using the right one, so it has to be like this. Now I know there's 1 hex set, 2, 3, 4, 5. I know 3 are missing here. So 3 zeros, continuous zeros. Okay. Now we talked about omitting leading zeros and omitting all 0 segments. IPv6 prefix length is same. It's just telling us, because IPv6 doesn't have a subnet mask. So for example, if I have 2001 DB8 ACAD A1. Now I don't know how many bits are there in the, where is the network ID? I need to know. So I can just say prefix length, how many bits are there network? For example, 64 bits are networks. Okay, well 64 bits, then I'm just going to write a leading 0 here as well. So 1, 2, 3, 4. Okay, so I know that this bit here is a network ID. Why? Because that's 4. That's 4. 8, 12, 16. So 1 hex set is 16. So another 16 is 32. Another 16 is 48. Another 16 bits, that's 64. So there I know that's a 64 bit. That's a network ID. So for example, I can use that as my network ID and give all my network devices similar ID, and they will be on the same network. They will be able to communicate with each other. 4, 5, and so on. All of them you need to tell what is the network ID, what portion is the network, and so on. Okay. Okay. Now, if I say /48 instead of 64, so 48. Now that's going to be 48. Sorry. So that's going to be 16. 3248. That's my network. That's my node. That here, 00A, is a part of the ID as well. It's a host portion. So this is my network ID. So the prefix thing from IPv6 is telling us what portion of the address is a network. Different IPv6 address types. We have, for example, first of all, we have unicast addresses. Unicast addresses are separated on different types of unicast address. First, we have a global unicast address. Global unicast address is like a public IPv4 address, which we use it for mainly for the public communication. Then linked local address. Linked local IPv6 address is similar to a PIPA, IP version 4 address. These type of addresses, they cannot communicate with anybody outside the local link. They can't go to the router to another network. It has to be within their own network. Then we have a loopback address. Well, loopback address is testing your network device has been installed properly. The TCP/IP stack has been configured correctly. The first address is reserved for the loopback. So : 1 is first address. Unspecified address : with nothing, just : means that if it doesn't have an IPv6 address yet, and it's trying to decide, it's trying to give IPv6 address to itself. Then we have a unique local addresses. Unique local addresses, they start with FC00 up to FDFF. Now, unique local addresses, they are like a private addresses in IPv4, but they are not preferred anymore. Well, they're not really preferred in IPv6. And then we have embedded IPv4 addresses. Embedded IPv4 addresses is addresses that they have IPv6 addresses that they have IPv4 embedded inside them. First of all, to configure the static configuration for global IPv6 address, we go to the control panel. Let's go to the control panel, use that VMware again, go to properties and select IPv6. So first you need to enable it and go to properties of that. Okay, we need to enable the card. So let's go and enable that. And go to properties of version 6 and give it a static IP address. So for example, 2001 DB8 ACAD A. That's my network ID. So : this will be, I don't know, 1 for example, and then /64, the prefix length. If I put the gateway will have to share this part. Okay, so I need to put, for example, that address as a gateway, or I can put the linked local address of the local router. Dynamic configuration is similar to static. In case we just choose dynamic configuration instead of static, and the device will actually ask the router for the network ID, the portion of the network ID, and it will create its own unique IPv6 address. Linked local addresses. Now, linked local addresses, they start with FE80. So you have to remember the linked local addresses, they start with FE80. You have to remember that. Now, each device, as soon as you enable an IPv6 address network device, it will assign itself a linked local address starting with FE80. It will be able to use its own MAC address. Now, the MAC address, for example, is, say it's AA BB CC 112233. This is the MAC address. MAC address. Now, MAC address is 48 bits. Now, the device wants to have first 64 bits and then another 64 bits for the host ID. So first is the network ID, and then the host ID. So 64. So network ID is a 64 and host ID is 64. What he's going to do is going to use its MAC address to have a portion of host ID if you leave it to default, if you don't configure it. So it's going to use the MAC address. So we'll use that here. But because it's 48 bits and it needs 64 bits, what it's going to do here in the middle, it will add FE, FF, FE. Then that will become a 64-bit address. 64 host address. All it needs to do is assign itself a network ID. Well, now for the network ID, for the link local, it's going to use FE80, this address here. So now he's got a link local address. He has configured itself. So from information that he has, he started with FE80 and he's used his MAC address to come up with the host portion of it. There you go. /64. And that's called a link local address. All the network devices, they're going to assign themselves a link local address. You can configure it. To configure it to the router, you have to go to the interface, for example. For example, you are in global config mode. You have to type IPv6 unicast routing to enable IPv6. And again, in the global mode, you have to access the interface, FA00 for example, and then you will be on this mode. And here we say IPv6 address FE80::1, for example. You don't want to use this MAC address and so on. And then you have to type link local at the back. So as you can see, if you don't want the device to use its MAC address as a link local, you can assign it itself an address. Static link local. Now, multicast IPv6 addresses. Multicast IPv6 addresses, they start with FF. So anytime you see FF, that's a multicast address. Connectivity verification, we use ping to test the local stack. So if we want to test our computer that is being configured correctly, so ping 127.0.0.1. Okay, that will work. So all we do now is we are testing our network card. We can ping any 127, so we can ping 255.255.254, for example. Same thing, we'll do the same. All 127 is reserved for this purpose. Now to ping, when we ping a remote device, for example, say we ping another device. So I don't know, ping www.bbc.co.uk. So I'm pinging a remote device. Now this is telling me how if I got a communication with that BBC server, and which I do, because I'm getting a reply from it. 212.58.246.95. Now that's all the information I find out. I got communication with them. I can communicate the time, how fast it's going, time to live, and so on. Now, but if I want to know exactly how the packets are going, then I'll have to type tracert. Tracert, or in the device routers, trace route, traceroute. But on the PC, on the local, on the Windows machine, tracert. Tracert, for example, put that address. Now this is going to go. It's going to find out that every hop to that destination. So we're going to see that every hop that is traveling. Okay, so ping connectivity to local LAN. We're testing the ping to the remote devices, and we use the traceroute to test the path. Okay, thank you very much for watching the video so far, and see you in part 2, subnetting IP networks. Bye.